Can you all see my presentation?
Yes, sir.
Okay.
Yes, sir.
So today, in today's lecture, we will talk about polynomials, and we will learn how to represent polynomials using linked list. Okay, single linked list. So let us look at how polynomials can be represented. So what we know about polynomials, that it is an ordered list of non-zero terms. Okay. So if we consider a polynomial like 2 into x to the power 4 minus 5 into x to the power 2 plus 6, then here we can see that here we have three terms, three non-zero terms. Okay. And in each non-zero terms, we can have two pieces of information, the exponent part and coefficient part. Okay. So the first term, 2 to the 2 into x to the power 4, here 2 is the coefficient, and x to the power 4, here 4 is the exponent part. Okay. Then minus 5 x to the minus 5 x square. So here minus 5 is the coefficient part, and here x to the power 2 is the exponent part. And then we have plus 6. Okay. So here 6 is the coefficient part, and exponent part is 0. That means if we write x to the power 0, then we obtain 1. So here exponent part is 0 and coefficient part is 6. So in this polynomial, we can see there are three terms, and when we represent these terms, then we will start from the lower exponent part. That means low exponent part. So here we will write the here we will write the non-zero terms in increasing order of exponent. So increasing order of exponent means, first, if we consider this polynomial, then we will write the last term first. Okay. That means when we will write the last term first, we use two tuple information. So two tuple information means, in two tuple information we will have the exponent part and coefficient part. So therefore, when we will write the first term in the representation, then first we will write the exponent part. Okay. Then we will put comma, and then we will write the coefficient part. So these two information constitute a two tuple information. Okay. For each non-zero term in the polynomial. So here accordingly we can represent the non-zero terms in increasing order of exponent. Okay. So therefore we can write 0 comma 6, 2 comma minus 5, 4 comma 2. So here highest highest degree of term will be written last. Okay. And lowest degree of term will be written first. So in terms of exponent, we can arrange the non-zero term in increasing order. Then if this is the ordered list of non-zero terms, then for each non-zero term or each two tuple information, how linked list can be used to represent the entire polynomial in terms of individual non-zero terms. Okay. Now here we can see that if we think to represent the non-zero term with the exponent and coefficient part using linked list, then each non-zero term will be represented by one single node. That means in the single node we will have two data part. Okay. Two information for data part, and one link part, because we need two data part, one for the exponent, another for the coefficient, and there will be one link part. So this entire information will be represented by a self-referential structure. So here the link representation of the polynomial can be represented by this figure. Okay. So here we can see that the first node is having two two information part, one for the exponent part 0, another for the coefficient part 6. Okay, and there is a link part, and that link part will contain the pointer that will point to the next node. So in the next node or the second node is containing two data part. One is the exponent part 2 and coefficient part -5. Okay. Similarly, we will have the exponent part and coefficient part in the last node. Okay. So for each non-zero term, we can use a node, and that can be represented by a self-referential structure. Now let us look at the self-referential structure. So here each term is non-zero term in the polynomial that can be defined by the self-referential structure. Okay. So here we are writing the self-referential structure for polynode. So type def struct polynode, and in this structure we have three different members. Okay, and first two members are coefficient and power, which will be type of integer, and another member that represent the link part of the pointer. So this link part will be type of structure polynode or struct polynode. Okay, and we have a structure variable uh, which has the same name as that of the structure name polynode. So this self-referential structure will be used for different operation on polynomials. Okay. So now if we perform some operations like polynomial addition, polynomial subtractions, then we can use this self-referential structure, so that this self-referential structure will be found to be useful to perform the operations. Now let us talk about the addition of two polynomials. Now, when we think to add two polynomials of a number of terms, then we could have uh, we could have two pointers, that is poly1 and poly2 of type struct polynode. Okay, and this poly1 pointer will point to the first linked list of which is constructed on the first polynomial. Okay, and poly2 is the second pointer which will point to the second linked list which is constructed on the second polynomial. Okay, and here we are using another pointer which is called polysum. So this is the double pointer. This polysum is used for the resultant polynomial. That means after addition of two polynomials, we will obtain a resultant polynomial, and that resultant polynomial will be pointed to by this polysum. Okay, this polysum is the another double pointer. This double pointer will point to the resultant polynomial. Okay. Now, apart from these three pointers, we can consider four other pointers like P, Q, R, S. Okay, and here we can declare new coefficient and new power. This new coefficient and new power will be the coefficient part and the exponent part of the resultant polynomials. Okay, so these two variables, new coefficient and new power, will be used for the coefficient part and the exponent part of the new polynomial or the resultant polynomial. Now what we are doing, we are initializing p equals to poly1. That means this poly1, this first pointer, now is assigned to another pointer variable p. Okay, and the second pointer which points to the second linked list which is constructed on the second polynomial is assigned to another pointer variable q, and we are making r equals to null. Okay, so we are making here r equals to null. Now we will use this while loop, and in the while loop we will keep a checking that whether p not equals to null or not, or q not equals to null or not. That means if both p and q are not null, then we can compare the exponent part of the first term of the first polynomial and the first term of the second polynomial. Okay, so that can be represented by p power and q power. Okay, now we keep another checking, so that will check the exponent part, whether the exponent part is found to be equal for the first non-zero term of the first polynomial and the first non-zero term of the second polynomial. Okay, so that power, that exponent part will be checked for equality. That means if the exponent is found to be equal, then we will assign, then we will add the coefficient part of the first non-zero term of the first polynomial and first non-zero term of the second polynomial. Then that means the coefficient part will be added, or both the coefficient will be added, and uh, this sum will be assigned to the new coefficient. That means the new coefficient becomes the addition of two coefficient of the first terms of the first polynomial and the second polynomial. Okay, so if this can be done when we will find the of exponent part of first non-zero terms of the first polynomial and the second polynomial will be found to be equal to 0. Okay, then new power will be assigned by p power. That means here either we can assign the q power or p power. Okay, so here p power is assigned to new power, or we can assign q power to new power. Okay, then we advance the pointer p for the next node. So that is why we are writing p equals to p next node and q equals to q next node. Okay, so here we are advancing the pointer both p and q for the next node, so that we can have the next non-zero terms for comparison. So if so this is for the equal. That means when we have the same exponent part in both the terms, then we can have these steps. Otherwise, if p power is found to be greater than q power, then we will assign q coefficient to new coefficient. That means the new coefficient becomes the coefficient of the second polynomial. That means coefficient of the first term of the second polynomial. Okay, because q power is exponent part of the q is found to be less than that of the exponent part of the non-zero term of the first polynomial. So therefore the new coefficient becomes the coefficient of the non-zero terms from the second polynomial. Okay, and new power becomes the q power, and then we will advance, because here we are using the coefficient and both coefficient and exponent part of the second polynomial as new coefficient and new power. Therefore here q pointer will be advanced. Okay, that is why we are writing q equals to q next node. Now, if p power is found to be less than that of q power, that means here q power, when the q power is found to be uh, p power, then what we have, we will find a new coefficient. That will be new coefficient becomes the coefficient of the non-zero terms of the first polynomial. Okay, and new power becomes the exponent part of the non-zero terms of the first polynomial. And similar to the earlier step, we will advance the p pointer. So that means here we can have three cases. In the first case, we will check whether the exponent part of non-zero term of first polynomial and second polynomial is found to be equal or not. Okay, if both are not found to be equal, then what we are getting in then we can have to check whether p power is found to be greater than q power or not. If this is not, if this is true, then we will follow certain steps. Otherwise, when p power is found to be less than q power, then we will follow another set of certain steps. Okay. Now suppose here we have after assigning after having the new coefficient and new powers, that means the coefficient part and the exponent part for the new polynomial or the resultant polynomial. Now we will check whether the new coefficient is found to be equals to 0 or not. Okay, so new coefficient we can keep a checking where we can check whether new coefficient not equals to 0 or not. If it is not equals to 0, then what we are doing, we are allocating a memory space for polynode. That means for the structure polynode, and we are assigning new coefficient to s coefficient, because here s is another pointer which will point to the node, and for that node we are allocating a memory we are allocating space in the memory. Okay, so that is why we are using this malloc function, and this malloc function will be allocating memory space of size polynode. Okay, and then we can assign the new coefficient and new power to s coefficient and s power. So here s coefficient is the pointer which will uh, the s coefficient will represent the coefficient part of the new node, and s power will represent the exponent part of the new node. Okay, because in the previous steps what we are getting the new coefficient and new power. That means the new coefficient values and new exponent values. So after having this new coefficient and new power, we have to construct the resultant polynomial using linked list. And since we are using the linked list, we have to create the nodes. So here this pointer uh, s helps to create a node using malloc function, and when the malloc function allocating memory of size polynode, then that memory space will be pointed to by this pointer s. Okay, and then what we are doing, we are assigning new coefficient values and new power values to s coefficient and s power. Okay, then what we are doing, we are keeping another checking, so that will check whether r is found to be null or not. If r is found to be null, then what we are doing, the node which has been created, uh, and having the new coefficient value and new exponent value, we are assigning this pointer to another pointer variable for polysum. Okay, that means now polysum will point to the that means when r equals to null means when uh, r is found to be empty. Okay, so R is found to be empty means if we repeat this process, if we repeat these operations or these steps on an existing resultant polynomial, then only R will be found to be not equals to null. Otherwise, R will be found to be null, and in that case, we will assign the s pointer to polysum, another pointer variable polysum. Okay. Otherwise, on existing polynomial, what we will do, we will simply assign the s to our next node. That means after the last node of the polynomial, that means here the last node, link part of the last node is represented by our next node. Okay, so our next node will be assigned by s. So here s pointer, because here represent the new node, or s points to the new node. So therefore, to make the to make the link part to point to the new node, we have to set the our next node to s. Okay, and then we are writing r equals to s. So why we are writing this r equals to s? So after set the link part of the last node on the of the existing polynomial to the new node, then we are writing r equals to s. That means now after assigning the new pointer to the next node, we are making r equals to s. That means the R pointer will now point to the newly constructed node after a link up between the last node and the new node. Okay, and then we are making s next node equals to null. So after having the new node into the existing polynomial, we are making s next node equals to null. That means the link part of the last node will point to null. Okay, so therefore we have to assign the null value to the link part of the last node. So therefore we are making s next node equals to null. Now suppose the first polynomial is empty and the second polynomial is non-empty. So in that case, so that is why we are writing here p equals to if p equals to null, and here while this while loop will be executed for q is found to be not equals to null. When p is null, q is not equals to null. Then we will repeat the same process. That means the malloc function will be used to allocate the memory space, and then that memory space will be pointed to by s pointer, and s coefficient and s power will be assigned by q coefficient and q power, because p is found to be null or p is found to be empty. Okay, and the second polynomial is non-empty. So in that case, the all the coefficient value, all the coefficients of the non-zero terms of the q polynomial, and the exponent part of all non-zero terms of the q polynomial will be assigned to s coefficient and s power. Okay, and rest of the operation will be same. That is, if r equals to null, then we will assign s to polysum pointer. Otherwise, our next node will be assigned by s. Then we will make r equals to s, and s next node will be assigned by null. Okay, and we will advance the q pointer. Now the in other case, we can have p is non-empty and q is empty. So in that case, what will happen? So in that case, the coefficient and exponent part of all the non-zero terms of the p polynomial will be assigned to s coefficient and s power, and then the same steps will be repeated here. So here when r is found to be null, then we will assign s to polysum pointer. Otherwise, our next node will be assigned by s. Okay, and we will make r equals to s, and next node we will make s next node equals to null, and then p will be advanced. The pointer p will be advanced for the next node. Okay, so that is why we are writing p equals to p next node. So in the first case, we found p equals to null, q equals to q not equals to null. In the second case, p is found to be non-empty and q is found to be empty. In both the cases, we will assign the coefficient and exponent part all the non-zero terms of the non-empty polynomial to the s coefficient and s power. And similarly here we will repeat the same process when we have second polynomial is found to be null, and the first polynomial is found to be not null. Okay, so this is the entire function definition for addition of two polynomials. You have class after 2:10 after
Yes,
this
sir.
class?
Yes, sir.
Oh, otherwise I will start. I will discuss this topic. It will take time. Should I discuss in the next class? Or if you give me 10 minutes, 15 minutes, then I can finish this part.
Till 2:15 you can do it, I guess.
Okay, okay. Now we will talk about the array representation of linked list. Okay. So in array representation of linked list, what we do, we represent an array using linked list. Okay. We represent array using, or in other way, we can say that we can represent the linked list using array. Okay. We can represent the linked list using array. Now in this array representation of linked list, we are trying to do, we are combining two different two different uh, two different data structure. So one data structure is array. Array is already, we know that array is static representation, and linked list is dynamic representation. Okay. Now both these representations are combined together for representing the linked list using array. So representing the linked list using array, here we say that array is representation of linked list. Now how it is done? Suppose we have been given a list of four numbers. Okay, four integer numbers: 10, -5, 0, and 99. Now to represent this list using array representation, now we have to think this list, the elements in the list to be stored into a linked list which is represented by two different arrays. Okay. Now to represent the linked list using array, we can consider two different array. So first array, we call the first array elements, and the second array is the next. Okay. And the first array will contain the all the elements which are provided in the list L. Okay. And the second array will represent the link part of each node. That means if we consider the elements, the the elements array will contain the data part of all nodes, and next array will contain all the link part of the pointers of the of all nodes of the linked list. Then it becomes easy to understand. Okay. So basically, if we say that element I represent the element of the ith node, then if we say that next I represent some link part, that means that link part will represent the link part of the element I node. That means the ith node of the link part of ith node can be represented by a next I. Okay. So initially all all locations in the next array will be occupied by -1. So this -1 means here the the node is when the first node, when these locations are occupied by -1, that means uh, the link part is link part uh, points to the points to null. Okay, that means the link parts will not point any other node. Or we can, in other way, we can say that when all the locations are occupied by -1 initially from the 0th index, that means the linked list is empty. Okay, a linked list is yet to be formed. And we are taking two variable. One is called the free, another is called the start. Now what is the significance of this free variable? So significance of the free variable is that this free variable represent the available part of the element array. Okay, available part of the element array. And what is the significance of start variable? This start variable represent the starting index of the element array. That means the starting index means if the first element of the list is found to be at the position at zeroth index, then start becomes zero. Okay, that means if the list begins from zeroth index, then start becomes zero. If the list begins from first index or second index or third index, so accordingly the value of the start variable will be changed. Okay, so if we consider that the list will start from the third index, that means 0, 1, 2, 3. That means the fourth position. Okay, third index. So first position is represented by zero index, then first index, then second index, and third index. Okay, then start becomes 3. Okay, so start becomes 3 here, because here the third index, the list start from the third index, therefore the value of the start variable become 3. Okay, so here since here the first element is to be inserted at the zeroth index, therefore the start becomes 0. Okay, and free will be 1. Free will be 1 means the available part of element array. Okay, when the first element of the list 10 is to be inserted at the zeroth index position in the array, in the elements array, then here we can see that the free becomes 1, because zeroth index position is occupied. So from which position the location, the position from which index the positions or locations are free, because after occupying the zeroth index, now from the first index we can insert the new elements. Okay, or we can insert the elements from the list L. That is why free becomes 1. Okay, and start becomes 0, because we have started from the zeroth index, therefore here start becomes 0. And at the same time, here we can see that the zeroth index position, in the zeroth index position in next array, we have assigned -1, because there is only one node. If we consider there is only one node, and the data part is represented by elements array, and the next part of the link part is represented by next array, therefore the link part of the pointer of the first node will assign to null. So, and to represent the null value, here we are assigning -1. This -1 will represent the null. Okay, now we are going to insert -5 element from the list L, and when the -5 will be inserted at first index position, then free becomes 2. That means from the second index the positions are available in elements array. Okay, and we are assigning 1 at zeroth index position in the next array. Okay, and -1 in the first index position in the next array. So that means here next array will contain all the integer values, because after getting the second node, the next part of the second node will found to be null. So therefore this -1 at the first index position in the next array will be found to be -1. So here free becomes 2, start becomes 0. Okay, so there will be no change in the start variable. And then we are inserting, or we are storing the 0 value or 0 element from the list L in the second index position in array elements. Okay, so accordingly the values in the first in the zeroth index first index will be changed in the next array. So we have been assigned 1 in the zeroth index position, and 2 in the first index position, and -1 in the second index position in the next array. Okay, and free becomes 3 because from third index position the spaces are available for the for insertion. Okay, so similarly, we can have the similar position when we will insert a new element in the array elements. Okay, at third index position, and free becomes 4 because fourth from the fourth index position, the space are available in the elements array, and accordingly the values at zeroth index, first index, second index, and third index will be changed in the next array, and still the start variable becomes 0. So this is the array representation of linked list. If we want to represent a linked list using array, and then we can have this mechanism where we can consider two different arrays, and we have to consider two variables. One is called the free, another is the start. Okay, and here element first array will contain the data part of the nodes of the linked list, and next array will contain the integer values which represent the link part of the nodes in the linked list. Okay, any questions from this part? Okay, so that's all for today, and there will be lab for group 3 on tomorrow. So tomorrow there will be lab for group 3. So it will lab will start from 1:30.